So the next characteristic that we're going to look at in waves is what happens when waves intersect, okay, when they combine. And that describes the principle of superposition. Okay, so when two waves intersect, they superimpose, and they can either add or they can subtract. And that's what we're going to be looking at for this video. All right, so the law of superposition says when two or more waves of the same type arrive at a given point in space at time, the displacement of the medium at that point is the algebraic sum of the individual displacements. So if you take a look at these two wave pulses over here, this is a smaller one traveling left, larger one traveling right. When they will intersect, according to the law of superposition, you're going to get a superwave. They're going to add together. So their amplitudes mathematically add, okay? And then the total amplitude is going to be the sum of the individual parts. All right, and then after the original information from that wave continues traveling in that direction, and the original information of that wave keeps traveling in that direction. Okay, and you can see this happen inside of your pool. You get reflections of waves off of the walls, and then it gets really choppy, and you'll get some super waves in the middle. All right, so I'm sure we've all have come across this in a pool, in a bathtub, or in a bucket of water. All right, so here's another diagram showing the superposition of waves. Here's that making that super wave where they constructively combine. Okay, constructive means that I'm adding constructively to add them together. And here I have a wave that is out of phase. Okay, it's the opposite. So you might have called this a trough. It's not really a trough. Okay, it would be that pulse, but it's pi radians out of phase. It's the opposite phase. Okay, it looks like a trough, and that looks like a crest. And when they're coming together, they're going to mathematically add. And what you see, because this wave amplitude is a little bit larger than that one, you see a small divot, okay, that is formed. And then they continue passing on. So it's the algebraic sum. That's positive, that's negative. The sum would be a little bit of a negative integer. So what happens when we get these strange pulses? Okay, so if you work in electronics, you can have square pulses, triangular pulses. All right, that waves don't necessarily have to be that rope, that pulse that we make in a rope that looks like that. They can be different. Okay, it depends on the disturbance that is making it. So here I have a triangular pulse combining with a square pulse. Which of these, A, B, C, or D, is going to be the result of that? So take a second and think about that. Okay, well, it can't be A, because that is a negative integer, and in order for A, that plus that shape that would have to be positive. So it can't be A. Okay, it can't be C. All right. This is probably the one. So B, because when they combine, it's just going to take a chunk of that out of that shape. And then after they continue passing, you get that formation. So how would you describe the intensity or power of the wave at the point of superposition? Okay, so remember, when they mathematically add up, like for example, this wave over here, what would happen to the intensity? Well, you'd have to square the amplitude. So the intensity becomes dramatically larger. So imagine this was 1.5 times the amplitude here. The intensity would be 1.5 squared. All right, so it becomes quite large. Now, something we've already talked about before is reflection, and that's a characteristic of when waves hit a medium that is more dense than the medium that it's in, it will reflect. Okay, so for example, if I created a wave or a pulse in a string, which I showed you in a previous video, and then that pulse is moving the energy towards the right, when it hits the wall, that wall will reflect that energy back. Now, it can do so in multiple ways. If that end of that string is fixed to the wall, according to Newton's third law of action and reaction, okay, it's going to apply a force in the opposite direction to send that wave back in opposite phase. Okay, so that pulse is coming in, and it's going to switch its phase. It's going to flip upside down and go back out that way if it's attached to the wall. Okay, so the rope exerts an upward force on the wall, and the wall is going to exert an equal and opposite downward force, which causes it to flip back. Okay, if I tied the rope such that it's not attached to the boundary at all, and it's free to move, what's going to happen is that wave is going to reflect off of this boundary in the same phase. Okay, it doesn't flip. Okay, so that's important to understand. All right, so when a pulse or a wave reflects off of a boundary, it depends on the density of the boundary. If the density is more dense than the medium that it was in, it would go through this thing called a phase change. Okay, if it's less dense, it just reflects in the same phase. Okay, that's one characteristic that we need to know. And then something that you can think about, what does the wave look like when it's reflecting? Well, here when it's reflecting, all right, as it's reflecting, it's flipping, all right, so it's going to be canceling. As I watch a pulse go into the wall, I would see it cancel out, and then the pulse would reform over here, because as it's going into the wall, it's immediately coming out on the bottom, and it'll be canceling due to the law of superposition. So you won't see a wave merging into the wall. You see it canceling, and that's the shape that you're seeing over here. It's canceling and then coming back out. Here is a diagram of 3 phases of electricity. Okay, so when you have AC current going into your wall, to smooth out the current, you have actually three wave patterns of electricity. Electricity has an alternating current that looks like this. Okay, it has a wave. All right, and so we use 3 phases in our electricity, and those phases are offset by 120 degrees. Okay, but when we talk about phase in IB physics, we talk about phase in terms of 2 pi or pi. So remember, what 2 pi radians is equal to 1 complete cycle. All right, oops, that's a good picture of that. So 1 complete cycle. Okay, so if I had 2 waves and they were exactly in phase, all right, if they both were in phase, they would be at the same part in the cycle in time. Okay, now these are waves that are in phase. Okay, now this bottom wave over here might have started a little bit later, but it starts at the exact same point. So we would say that these 2 waves are in phase, or they are on the order of 2 pi radians difference in phase. They're always going to start at the same point in the same cycle. Okay, so if I look at these different wave patterns, they're not 2 pi, they're starting at different places. Okay, they all start at different places. All right, so what is their relationship in terms of phase, in terms of 2 pi? Okay, so if it's a 120 degree difference, okay, in phase, I can figure out their phase difference. I can figure out the phase difference by figuring out how many pi radians they are different from each other. So if I take 120 degrees divided by 360 degrees times 2 pi in a full cycle, that would give me 2/3 pi. Okay, and so we would say that each of those phases are 2/3 pi out of phase. Okay, so all 3 of those, between phase 1 and phase 2 would be 2/3 pi out of phase. Between phase 1 and phase 3 would be 4/3 pi out of phase. Okay, and so on and so on. So you can describe, when you're talking about when is that second wave coming out, is it in phase or out of phase, and by how much? We describe that in terms of what fraction of 2 pi radians is that wave in phase or out of phase. Okay, and that's that for that video.